And if we have an event, let's say something is happening. There are 3 different events, and all of them have 5% probability. There is a dot here. So there is a very high probability event, which is saying that nothing is happening. Then there is like a 5% probability something happened, then something else with the same probability might happen, or something else with the same probability might happen. So if we are gonna send it over a channel or a storage, we have to somehow associate binary codes to these binary codes that would be possible to read and write without confusion. So if we write something, we have to be able to read it and read the same information. So we realized, okay, we can do a fixed length. So for 4 events, we can associate 0, 0 with the first event, 0, 1 with the second event, and so on. And if we have a stream of events like this, that it makes sense that the event 0 is happening much more often, and then there are some 1s and 2s and 3s in here as well. And if you're encoding this in the format that we just talked about, the 0s would be converted to 0, 0s, and the 1s will be converted to 0, 1s, and 2s 1, 0, and the 3s 1, 1. So this representation, if we can see a little bit here to the right, this representation makes sense that has an average length of 2, which is kind of obvious since you're encoding every symbol with 2 bits exactly, you get an average of 2 over each symbol. Then somebody comes over and say, okay, the events do not have the same probabilities. So what if I do something smart? What if I do a trick? And he introduces something like this. It says, okay, the first event that's very high probability, let's associate a single 0 for that. And the 3 other events, let's associate a 1 with that. And if one of them happen, we send 1, and then it's 2 bits, mention which of them happened. So it's easy because when the event 1 happens, you only send 0, and when event 1 doesn't happen, one of the other 3 happen, you send 1 and then identify which of those has happened. So in this fashion, all the 0s here will become single 0s, and all the 1s will become 101, all the 2s become 110, and all the 3s become 111, right? So it makes sense, and it's easily decodable since you read each bit. If it's 0, you say, okay, 1 event of 0 happened, or if it's not 0, then you read the next 2 bits and determine which event has happened. Okay, on average, if we calculate the average length for this one, we can see that, let's come here, we can see that there is a length of 1 with a probability of 85%, and length of 3 with probability of 5%, again for the event 2, 5%, and event 3, 5%. And on average, it will be 1.3. Makes sense. It's much better than the average of 2, since we are associating smaller length to higher probabilities. So this is just a heuristic, but they thought about this in the old times, and they said, okay, well, why don't we have a better method, a systematic method for this? So what they came up with was, okay, whatever that can be decoded in this way, which is reading and extracting information, is anything that's in a structured tree. So if you're reading the sequence from left to right, you have to be able to know where the section has entered. So for that reason, you cannot have, if you have 0, 1 as one of the code words, you cannot have 0 or 0, 1, 1 as other code words, since there shouldn't be an ambiguity. So when you read the first 0, you have to know whether I should stop here or I should continue to end up getting X. So these are only one of these can happen. And if you take a little time to consider these code words, these are a starting point of the other ones, and if we want this to be valid, so none of the code words should be starting point of the other ones. And when you see something like that, you realize, okay, I can create something like that and check that very effectively with a tree structure. For instance, if I have 0, 1, I can consider 0 going left and 1 going right, and I can associate that symbol over here. Here, checking that something is ambiguous or not is a lot easy. You only can have to see nothing is here, so there shouldn't be anything just 0 or anything starting with 0, 1 something. So this branch ends here. So it's when you have something a tree structure, it's very easy to check these situations that things can be decoded. Okay, then comes the problem how we can create something that's actually optimal, something that has a good compression scheme for us. And then we see, okay, we have these probabilities for our own example. We have these probabilities, and we know someone has to be on the lower part, on the high length part, because somebody has to go there. And since we know that the higher length should go with somebody that has a low probability, intuitively we can say that, okay, let's pick up the last two and merge them into a single branch. So that's what we do. We pick up, so we sort all the probabilities and we consider the last two and we merge them into a single branch. Then we see, okay, we have different events that have, one has 85%, one have 5%, and the other two on some have 10%. So the same argument happens. So the two least probabilities should be merged to create another branch, something like this. Or it might be like two complex branches like this joining together. It doesn't matter. But in our case, it's like this. So the two least probabilities are merged together and something like this is created. So this has 85% and this has 15%. And then we still have the same argument that there has to be, lowest probabilities should merge and create a higher level, and you get something like this. Okay, sorry. You get something like this. This is very intuitive way of creating this tree, but let's see if we what's the code words for each guy. So over here, if we can say the first event is encoded as 0, so since it's 1 left, the second event is 1, 0, and the third event is 1, the first one, the second one, and then a 0. So 1, 1, 0. This is the third event, second event, first event, and the last one is 1, 1, and 1. So this is, as you can see, none of them is the starting point of the other one, and these are all valid. So if we calculate the expected length or the average length, we have one length 1, which has 85% probability, length 2, 5%, length 3, 5%, and length 3, the last one, 5%. And we get an average of 1.25, which is better than the previous heuristic. Actually, they have shown, it can be shown that this is the best, this approach is the best that you can get with certain limitations. And it's also shown that the entropy is always less than the expected length of the Huffman code that we just created for every kind of event. And you can easily decode things in a left to right manner. So we can, if we have this kind of encoding, you can read the first one, traverse the network this way because this is the 0, and get an event 1. Then again, a single 0, event 1. Then 1, you come here. Another one, you come here. And there is a 0. You go left, you get a 3. Then there is 1. There is 0, 2. So the next one, 1, 1, this one, and you get the 4 and another 0, which is 1. So it's very easy and straightforward to decode with this kind of decoding schemes. So now we have to talk about a little bit about what are the limitations. So there are multiple limitations as we talked about. One is for Huffman coding that we just talked about, is the entropy. You cannot have something that's doing better than the entropy, and it's also proven that you cannot do worse than entropy plus 1. So it's pretty fair. But there is another limitation that it's not always talked about. That's the obvious one. For every symbol that you're encoding, you're sending at least 1 bit. And this is something that we most of the time we don't talk about. And this is a limitation. If the it doesn't matter, the entropy is 0. If the entropy is even very close to 0, you're sending at least 1 bit per symbol that you're encoding, and that's a strong, huge limitation. Another limitation for Huffman encoding is you have to actually send somehow the Huffman tree. Somebody has to tell the receiver or whoever is receiving the file on the disk that this is my tree. If they don't know, they cannot do so. At least either the probabilities or the structure, the structure of the tree should be sent to the receiver. And there are problems that this is a little bit overhead, and we have to address this in the further next videos. And also the way that we talked about decoding is not very clear, so we have to have a better way of decoding. Can we decode better? And we answer this as well in our further videos. Okay, that's for Huffman coding, and we will cover these in the future videos. Thank you for listening and watching, and see you next time.